In this video, I'm going to look at the question, what is a p-value? I'm going to do one simple example of finding the p-value, but this video is mainly about the concept of the p-value. The p-value is a measure of the strength of the evidence against the null hypothesis that is provided by our sample data. The p-value is the probability of getting the observed value of the test statistic, or a value with even greater evidence against the null hypothesis, if the null hypothesis is in fact true. So first of all, the p-value is a probability, and it is a probability calculated conditional on the null hypothesis being true. The definition is a bit of a mouthful, so let's look at an example. Suppose we wish to carry out a test of the null hypothesis that mu, the population mean, is equal to some hypothesized value. And suppose that we are sampling from a normally distributed population where sigma is known. If that's the case, the appropriate test statistic is this Z test statistic. If this null hypothesis is in fact true, then mu is equal to mu naught, and this statistic will have the standard normal distribution. And so over here I have the distribution of that Z test statistic if the null hypothesis is true, and that is the standard normal distribution. Suppose, for the sake of illustration, that we get a sample and we find that the value of the test statistic is 2.05. 2.05 is right about here on the curve. In this case, our alternative hypothesis is that the population mean is greater than the hypothesized value. And so large values of this test statistic are going to give us evidence against the null hypothesis. The farther out in the right tail that this test statistic is, the greater the evidence against the null hypothesis. And recall that the p-value is the probability of getting the observed value of the test statistic, or something with even greater evidence against the null hypothesis, if the null hypothesis is true. So in this case, that's going to be the probability, under the null hypothesis, of getting the observed value of the test statistic, or something even farther out in the right tail. Or in other words, the area to the right of our observed test statistic. That is going to be the p-value here. And if we went to software or a standard normal table here, we'd see that this is approximately 0.020. In this particular setting, the farther out in the right tail the observed value of the test statistic is, the smaller the p-value and the greater the evidence against the null hypothesis. And this is true in the more general setting. The smaller the p-value, the greater the evidence against the null hypothesis. If we have a given significance level alpha, then we reject the null hypothesis if the p-value is less than or equal to the significance level alpha. Or we could say that the evidence against the null hypothesis is significant at the alpha level of significance. And so we could consider alpha to be a cutoff level for significance. In the real world, we're not always going to have an alpha level given to us. And then the situation is not quite so simple. If we do not have a given significance level, then the situation is not as cut and dried. But it might help us come up with reasonable conclusions if we understand the distribution of the p-value. For continuous test statistics, under the assumptions of the model, if the null hypothesis is true, the p-value will have a uniform distribution between 0 and 1. And, a little loosely speaking, any value between 0 and 1 is equally likely to occur if the null hypothesis is true. And so, if the null hypothesis is true, on average, we're going to get a p-value of 0.5. But it also might help with our interpretation if we know something about the distribution of the p-value when the null hypothesis is false. So let's simulate 1,000,000 samples to investigate the distribution of the p-value in different scenarios. Here I've decided to test the null hypothesis that mu is equal to 0 against a two-sided alternative. The samples have 20 observations in them, and sigma is equal to 5. And we're sampling from a normally distributed population, so we'll be using a z-test. And on this slide, there's 3 scenarios illustrated. In this first one, mu is equal to 0, so the true value of the population mean is equal to the hypothesized mean, or in other words, the null hypothesis is true. Here's a histogram of the 1,000,000 p-values corresponding to those 1,000,000 different samples that I simulated. And as we can see, that p-value seems to have that uniform distribution. The theoretical average value for our p-value when the null hypothesis is true is 0.5, and here, in the simulation, we also get a value of 0.50 to 2 decimal places. Down here, I'm going to look at 2 situations where the null hypothesis is false. In this first one, the true value of mu is 1, and we're still hypothesizing that it's 0, so the null hypothesis is false. I simulate 1,000,000 samples where mu is actually 1 and find out what the p-value is and plot it in this histogram. And here the distribution is not uniform anymore. The distribution is moved towards 0. And in this situation, for those 1,000,000 p-values, we find an average p-value of 0.39. In this other situation, the null hypothesis is still false, but mu is even farther from the hypothesized value. And this histogram of p-values is shifted even farther over towards 0. And the average p-value we got here is 0.18. And so we can see here that when the null hypothesis is true, the p-value has a uniform distribution between 0 and 1. And when the null hypothesis is false, the distribution of the p-value moves more towards 0. So we're going to be more likely to get p-values near 0 when the null hypothesis is false than when the null hypothesis is true. We saw here that the distribution of the p-value depends on what the true value of the population mean is. It's also going to depend on the sample size and the standard deviation in this case. To illustrate that, let's see what happens when we increase the sample size to 50. The only thing that's been changed in this simulation is that the sample size has been increased to 50. We can see here when the null hypothesis is true that distribution of the p-value is still uniform between 0 and 1. And when the null hypothesis is false, the distribution of the p-value still again moves towards 0. But because of the increased sample size, down here when the null hypothesis is false, the p-value distribution has shifted even farther towards 0. Over here, the average p-value is now 0.27, and over here, the average p-value is now 0.04. When we have a greater sample size, our tests are going to have greater power, and the distribution of the p-value is going to be shifted more towards 0. The overall lesson I'm trying to get at here is that we're more likely to get p-values close to 0 when the null hypothesis is wrong than when the null hypothesis is right. And so the smaller the p-value, the greater the evidence against the null hypothesis. I'm going to give a very rough guideline here. It has to be a very rough guideline because what we feel is strong evidence against the null hypothesis depends on the situation at hand as well as the p-value. But as a very rough guideline, if the p-value is less than 0.01, we can say there is very strong evidence against the null hypothesis. If the p-value lies between 0.01 and 0.05, well, there's starting to be strong evidence against the null hypothesis. If the p-value is between 0.05 and 0.1, there's some weak evidence against the null hypothesis. And if the p-value is greater than 0.1, we say there's little or no evidence against the null hypothesis. This does depend on the setting. If the p-value is close to 0.1, in some situations we may feel that that has a hint of evidence against the null hypothesis. For example, if our p-value is 0.11 or 0.13 or something like that, in some situations we might view that as a hint of evidence against the null hypothesis. But for most practical cases, once the p-value starts getting up into the 0.2 and 0.3 range and greater, we say that there is no evidence against the null hypothesis.